talked about Euler's method a little bit yesterday in that video. If you haven't watched it yet, you got to get that done. This is the first of quite a few different methods that we'll use, but they'll all be pretty much linear. Okay, so they'll all be this idea that you're going to start with some y naught, and you're going to add to that some slope, right? And then times some delta x. Okay, and then that's going to give you an approximate, let's say y1. Okay, and then you're going to just take and reiterate. You're just going to keep iterating this function over and over and over again. But the difference is going to be how we compute these slopes. So yesterday we talked about Euler's method. It's very straightforward. It's very easy to do. But later on we'll get better slopes. We'll do one called the improved Euler method. One's called there's like a bunch of different Runge-Kutta methods that you do. It's just different ways of finding a better slope. That's the only difference between all of them, really. Okay. So you're saying that you're starting at one end of this delta x and you're heading to the other end of it. You're only taking into account what the slope would be on this end. The improved Euler method takes it and looks at over both ends and tries to find a better average, if you will, rate of change. Okay, and then the Runge-Kutta method does it, but it does it like at 4 places is how it does it, and it's kind of weird. So it's kind of cool, but it's really the only difference will be this guy right here. Okay, in all of the methods, so they're all linear in essence. The difference is just how we find that slope. So it's pretty easy. So the one we did yesterday, or ones we did yesterday, was something like, I don't know, dy dx. Let's do 3 dy dx. Plus 2y equals 3x. Yeah. Hey, is that linear? I'm sorry, is that linear? It is linear. Is it separable? No. This one is not separable. How do you know, Mr. Groom? Because 3x minus 2y, and of course, I'm going to divide them by 3, and I'll just do that right now, is this fella. So, oops. There's no way to solve this yet. You don't know how to solve it yet. We'll get there pretty soon. Later this chapter, actually. But for right now, you don't know how to solve this guy. So, it's not separable. So there's only one way to go from here for us. And that is we would like to know what happens to this guy. Let's say, suppose I knew his f of 0 is 100. What I'm going to do is I'm just going to do an approximation for this thing and see what I end up with. Now, being as I don't know what this function is actually going to come out like, I'm going to overdo my step size. I'm going to probably do 0.001 or something to make sure that I get a pretty good sized amount. What's kind of cool is you can kind of sneak up on it if you do 0.01 for a step size and write the answer down, and then do 0.001 and see how much it changed. But if it changed a lot, then you might want to go 0.0001 and see if you can sneak up on it a little bit. Again, with Excel, it's not that big a deal to us. But maybe we want to know what is f of... Let's do f of 3. That's still going to kill me because I'm going to have to drag this down a long ways. Okay. But anyway, here he goes. Now, if you are insisting on doing it in... I'm going to do this one like if I was doing it in Google. So I'm going to do the F4 bit and all that. All right, so where did I start off with? Was it 1,000? 100, yeah. Oops, what am I doing? Don't put that there. I'm sorry, this is the way I had it laid out. X, Y, slope. And then over here I could do step, whatever. And let's say I do 0.01. And I don't know what that is yet. I kind of do, but I kind of don't. And then, so initially we're at 0 and 100. And so my slope equation was equal to, was it x, right? Minus 2/3 times y. Bam. Nice. Now, we're just going to count by the steps. So it's going to be where I started from plus the step. And if I do it this way, I don't have to name it, but I have to use the dollar signs. Nice. And just drag that baby down a ways. Clearly, I drag it down to 300 if we're going to 3. Yes.
The only part I'm confused about is why do you have to do the dollar signs like that?
Okay. Because it stays in that little box. Okay. So that cell I want to lock in. So where's the 0.01? I'm adding 0.01, right? So because I want to add 0.01. Well, here's the thing. I could literally write plus 0.01 if I wanted to. Okay, I could do that if I wanted to, but I don't want to because on the very next problem I'm going to change it to 0.001. So I want it to update. So whatever's in that box is going to go over there. Okay, but I can either name it step And I could just do plus step, or I could do it with the dollar signs. Either
The
one.
problem is in Google Sheets, you can't.
In Google Sheets, you have to use the dollar signs because you can't name cells in Google Sheets.
You can actually.
Well, you can. It's not as easy, and I don't want to go through it. And I don't care anymore. So back in the day, we used dollar signs. It still works in Excel. And if listen, it's better than doing it by hand. It's better to do it by hand. It's just not something I want to do. It's not something I want to do. All right. So here it's going to be equals the previous amount, yes,
Yeah.
plus our plus our slope times this fella. But again, I don't want that guy to change. So put the dollar signs on it. Okay? Y equals mx plus b. Well, it's kind of the b plus the mx, right? All right. Oops, there it is, whatever. Oh, that's cool. Drag this down to here like so. Oh, notice we have a negative slope, do we not? What's happening to our slope? It's getting less negative. So, Corey, do it again. Corey's going, it's going to go like this maybe? What? Like maybe like it's approaching a what? Maybe. And so what should our y's do?
They should tend to go towards a number.
They should maybe tend to go towards a number. So let's see if this is going to work. Double click. Give it to me. Oh, for crying out loud. Double click. There we go. Oh. Oh. It's like we're zooming in on something. Still going down. Oh, 15-ish. Okay. Mr. What would happen if we kept going further? I don't know. Let's find out. I'm going to have to do this in a minute anyways to drag it down because I'm going to go 1,000 instead of 100 just for fun, but might as well just try it, right? Because what else you got to lose? I don't know, just for
Go
fun.
to 3,000.
Might as well go to 3,000 on account I'm going to go there in a minute anyway.
Change it to 0.001, then it'll be
Mhm.
in the right spot.
How you all doing today?
Yesterday I got to 20,000.
Take
That was a long time. It took me 20
There's got to be a better way to do that. You
Yeah.
spent a minute
There-
and a half in the
let-
video actually doing this.
That's
Well,
nice.
he talked. Well, he was, but he was just doing this. Yeah. How stupid he was.
Weird. Hey, weird. Hey, weird. Hey, weird. Let's no, well, yes, but wait. But more importantly, somewhere back up in here, we're still, it looks like we're getting awfully close to, we're going back, so we've gone down and now we're starting to come back up. Did we ever hit 0? Did we ever hit 0? I don't know. I'm interested. Come on.
Oh, sorry. 0.1, oh, negative.
Oh, coming back up.
That's zero slope.
Wait a minute, how did you know that? Because our slope was 0. Our slope was 0, so that means at some point in there you had to have reached that's pretty darn close to its minimum, yes?
Yeah.
Nice. Voila, whatever, yay. Does that make sense? So it was decreasing, now it's coming back up again. Okay, yeah.
So when you have a positive and a negative, and you know that there's something between that's intermediate, right?
Intermediate value.
Right on?
You guys are going to have it.
Nice. Anyway, so it looks like somewhere right around this neighborhood, 8.55-ish, right? Minimum that it gets to, and then it starts coming back up again. I don't know, whatever, so you can see this. Now, again, let's go back to the top.
So this one then has an asymptote there instead of minimum.
Sure, it looks like it has maybe just like a minimum there, and not an equilibrium solution, in
Yeah.
other words. Yeah. All right, let's go down here anyway, see what's up. Let's just, I don't know, we'll just try something out here. Then we'll go look at something a little differently. I'm going to drag this down a ways because that's pissing me off. There we go. Halfway there. What?
So this is only based on my observations.
Yes.
What's going on?
Yes.
So
Shh.
does not passing the horizontal line does have anything to do with the equation not being separable?
No.
It doesn't.
What passes for the, no. So the only way you know it's separable or not is if you can divide or multiply I get all the x's on one side and all the y's on the other way. That's all separable means.
Why do you have to
So, but it doesn't.
Because you can't subtract. Shh, that's a good question. Well, as soon as I pick up my pencil, it's going to stop, so I can't do that right now. But I'll show you in a minute.
Because I was wondering when you said it was non-separable, I was like, why don't you just add it in a time?
Ooh.
Oh, you know, oh, that's why, hold on.
Because you got to get your dy dx.
dy dx
Yeah.
plus value. No.
Mm-hmm.
Got it.
Mm-hmm. We're getting there, Danger Dan.
Not one time in this video, so we're
Meow.
yesterday, like 1,000 down.
Did I really?
Yeah, when you're going down to like 10,000, you're like,
That's just what I do.
it's okay, because I was trying to get my 20,000 sell.
Yeah, I forgot what it was on that first time. But okay, so write that down. 16.07. Write it down.
Hopefully ever actually
You went to
solve it.
8 last time.
That was it, like.
No, I know. But I'm going to change this to 0.01. And then I'm going to go back down and look at. Oops.
Oh, 1.
I have
Oh,
1.
man. Oh,
Oops.
you're cut.
Whoa, Betsy. 300.
Up to 8.
15.9? Oh, at 3. Yeah, 15.9?
16.07?
So it didn't change the wheel a lot, yes? If it had a violently big change there, I go a smaller step size yet. Okay? But again, Euler method's kind of the right-left sums of this world of doing this crap. Okay? You show right-left sums, like, oh, that's cool, let's do something better. Okay? So it's the first one of the bunch. But again, I like your question there. It was, you know, like, over here, you can't, like, now, for instance, you cannot get this guy rather, over here, or you can, but if you do, then your dy dx is not separable, outable. Thanks, man. It's good to see you. So it has to be a situation where you can divide some of this mass over the other side, or multiply it over the other side, and get your dy dx back over. This one happens to be what's called linear. Okay, we're going to solve them a little bit later on. It's going to be kind of fun. It's going to be good times. Sort of. It's kind of fun though. They're not too bad. There's a little trick for that. So we said this is about, what did we say, 15.9 or 16.07 or something. That's a pretty good approximation for it, I think. Okay. Ooh, question though. I feel like, it seems like maybe, if this were set equal to 0, well, what do I know? Well, I know that x would equal 2/3 of y. Sure looks like, maybe? Well, that's weird. So when x is 2/3 of y, we're going to have like a 0 slope or something maybe in there? Interesting. Let's go see if that holds true. Somewhere down here we had a 0 slope. Let's see if that relationship is true. Somewhere. Where are you? So if 8.55 times 2/3, yeah, it's probably in that ballpark-ish. Probably in that ballpark.
5.7.
What?
5.7.
Boom.
Oh, there you go. Oh, I was like, what are you doing? Yeah, I got you. 5.7. Yeah, there it is. Cool. So it's kind of nice. The relationship holds. What's that going to be? It's going to be any time that x is 2/3 of y, right? So it's not going to be an answer like before, like when y is 100. It's going to be, whatever. All right. Okay. It's linear because of how it's laid out. Okay, so we'll talk more about this later on. But when it's in this kind of format, that's a linear format. That's called. And so when it's in that format, then there is a method of madness, a way to solve that. Okay, so it's good times. All right. Now, we talked about this before. We talked about equilibriums, and we talked about, let's say, this one here. I'm just going to show you this because your book does it words it slightly different than the way I do it. So our equilibriums here at 0 and 3, right? 0 and 3 are my equilibriums, right? So, okay. And if you're less than 0, that's going to be a negative slope, I think, right? And if you're looking at a slope field, it would be looking like a bunch of these, I suppose, something like this, right? And if you're in here, like 1, that's positive, so it's positive slopes. or again, you're going to have slope fields that look kind of like this business. And obviously what's happening here, they're going to come up and do some of this business, right? So in here you've got this classic, this kind of a shape going on, right? And down here you've got some of these guys going on, depending, of course, where you started, but they're going to look like that. And then up here, when they're positive, this is going to be negative slopes. So it's going to be the classic, exactly, logistic function like that. Negative slopes. Now, I like to refer to these, again, this is stable equilibrium. It's stable. Okay? This is unstable. Now, just be aware that your book, it's just weird. I've never seen a book do it this way before. Later on, when we get into two populations, like rabbits and foxes and stuff, we'll talk about things like spiral. We'll talk about sinks and nodes and stuff. But usually in one dimension, when there's just one population, normally we just talk about stable and unstable. But just so you know, your book talks about this being a sink, and this one talks about this one being a source. Okay? That is, everything is coming down to the sink, and everything is springing forth from the source. Yes? So unstable is a source, it's blowing away from it. Stable, everything's coming towards it, therefore it's a sink. Yes?
What's the point of actually, like, obviously the lines come together, like two lines come together with the stable one. What's the point of actually labeling them? Like, is there...
No, yes, we like stable and unstable equilibrium because it helps us as a person to study this kind of crap. We go, oh my gosh, this is exciting, because if I see this deal here, I realize that everything's going to tend toward this 3, no matter what I do. It's hard to screw this one up, versus if this was a extinction explosion, this would come down and this would go up, and you're like, I have to really tend to my populations. I have to really pay attention to what's going on. This one here, you can't screw this up. It's like falling off a bike. You cannot really screw up falling off a bike. It's the natural thing to do. Okay. Down here, unstable source, again, it's the idea of just, how do you manage things, right? So if you're doing managing a population, just be aware of that. And then this one, which we called, semi-stable. That's the way most books refer to it as, right? This one they just call a node. So just be aware of the terminology. It's not a big deal to me. Semi-stable. Again, I prefer this semi-stable, stable, and unstable when you're talking about one population, and then later on we'll get into nodes and we'll get into sinks and sources a lot more when we get into two-dimensional stuff. So there's two populations going on. It makes a lot more sense then. But I guess from what I can tell, they just kind of want to make sure that the terminology is the same throughout the book. So just so you know that when you go to read it. Now, here is a question. You've seen this guy. This guy we are very familiar with. Right? It is clearly logistic. Everybody knows it. Everybody knows it. We know that our equilibriums are at 0 and a hundo. Obviously if you start out with 150, it's going to drop down to 100. In the real world, it actually would probably end up dipping under 100, and it'd fluctuate all around 100. You're not going to have anywhere 100 fish in a pond, and that's rare. So, or 100,000, whatever that stands for. Okay, but sometimes it's going to be really high. Can you put it on my desk?
No, just
question.
This seems wrong.
Where?
Or secant of that.
Oh, thank you, thank you. Oh, let's fix that. Hey, on the one where it has square root of 2 over 2. Can you just make it square root of 2 for me? Sorry, my bad. Do you see where it says square root of 2 over 2? In the secant column? Just make it square root of 2. That's my bad. You have a hard time doing it the other way. Alright, so here we are. Anyway, it's going to fluctuate around 100, right? That's our equilibrium, but you might get your ass a little high, a little low. This is life, that's how it goes. So, but we know how to solve it. Of course, it's separable. Oops. 100 minus y, like so. And again, I'm just going to review this real quick because that part's pretty straightforward. But the next thing is what we're going to add to this is it makes it a little more fun. So, what happens now? All right, well, 1 over y, 100 minus y, a over y, b over 100 minus y. So you're going to get 1 equals a 100 minus y plus by. So if we put in 0, you're going to get 100a, so a is 1/100th. And put in 100, b is also 1/100th. Nice. Right? Right. Which means that I could rewrite that as 1 over 100, 1 over y, plus 1 over 100, 1 over 100 minus y, dy, dy, equals 0.02 dt. And then, of course, I'm just going to go with 0.01. It's going to make my life easier. ln of y minus ln of 100 minus y. Now, if you're not sure why it's minus there, ask now. Substitution, yes? So if you let u equal 100 minus y, then du is negative dy, right? There it is. That's kind of a big deal. All right. Now what do I do? Well, I would multiply everybody by 100. Yes? Times everybody by 100, and combine your logs at the same time. 2t plus a constant. Am I right?
But it is now a different constant.
Yes. E to the. All done?
Yeah.
You sit on my desk, and then just have some time to work. Okay? By the time we, yeah, okay. So about let's say 5 or 6 more minutes, you people. That's about right. That'll give you 20 minutes left in class. That means you've been working for half an hour. It seems kind of slow. Let's go pick up the pace. Pick up the pace. You can do it. I'm not rushing. I'm just saying. So,
I'm not rushing, but hurry up.
get the lead out of your britches. All right. Right? This is taking a sweet time to do, but whatever. What else have I have to do today? See? See? Es muy bueno. Just distributate. Plus her over to here. Look at it.
Yeah.
Do you need the C over there? If you have 100 C.
Technically, no. Technically, no. But my very next step is to divisiontate. Yes? And this is where the big kids take it a step further. So the big kids don't like this with that C on top and the E to the T on top. And they don't like all that garbage. So what they do, this is the big kids, of course, they divide top and bottom by C, E to the 2T, yes? If you do it on top, you do it on the bottom. And so you get 100 on top. And on the bottom here, you're going to get 1 over, I'm just going to write 1 over C, and then I'm going to write e to the negative 2t. You with me on this? Plus 1. Right? So it's just so when I divide this out, it's going to be 1 over C e to the 2t, but I could rewrite that as e to the negative 2t. And then 1 over C is just a different constant, yes?
Yeah.
And then plus 1.
So it's going to be 100 over C E.
There you go. So what happens to this thing? What is the limit? What is the limit as t goes to infinity here? That's why we write it in this formula. If you write it in this formula, what is the limit of this thing? Well, this piece goes to what? Goes to 0. Yeah, 100 over 1, 100. Okay? So if you start this equation with anything, it's like, if you start it with any...
It doesn't go to 0, does it?
Yeah, it does.
Oh,
Even
yeah,
negative
yeah.
2t.
That's a negative. Okay, so
Boom.
it's gonna be negative.
Boom. Boom. So here's the thing. That's assuming that where'd you start? That this C that you got came from a value that makes sense, right? So like, you know, somewhere either above or below 100, doesn't matter, but positive. Okay, it's kind of sort of negative fishing upon. If you start with the amount of fish that makes sense or what have you, this thing will always head towards 100 as time goes to infinity. That's why we like it in this format. Okay, great. Now I lost my train of thought. Oh yeah, so here we are. Suppose I wanted to fish for some fishies. Well, then I feel all done. All done. Okay. No hurry. Take your time. well, for another 5 minutes or so. Now, the equation was this feller, yes? dy dt is 0.02 y, 100 minus y. Suppose I take out some fish. Some H. Why H, Mr. Groom? Because I'm going to harvest some fishes. Nice. But allow me to distributate. Yes? This is quadratic, am I right? Well, only if you are really into masochism, then yes. You can do it this way. I personally, I would use quadratic formula.
Yeah.
Okay? You do what you want to do.
No, we use it.
Don't let me stop you. Now,
I can put this away.
so, and no one's shocked. Okay, now, so y equals what? So opposite of b, plus or minus, square root of b squared minus 4 times a times c, all over 2a. Let's crunch this, shall we? What does this come out to be under here? So oh, wait, that should be negative h, Mr. Grimm, you idiot. I didn't finish my deal, I guess. So if you would please, that's going to be 4 plus, no, minus 4 minus 0.08h, yes? Okay. Are you ready to have your mind blown just a skosh?
I prefer, yeah,
Seriously, I think you will. Okay, how about this one too? So I made a new batch of ginger ale the other day. It's in my jug that Dallin Opdahl made for me. And got my little cork in it. And so put it in there, and of course it fizzes and it does its thing. And it always shoots the cork out, so I'm not shocked. And I have an air bleed off valve, but it's on a bigger cork. I need to get a smaller. I need to get a cork with a smaller hole in it, but whatever. It's long. So anyway, I kept shooting the thing out. Well, okay, so I knew it shot it out, so I stuck it back in. Last night I poked the cork in just a little further to see how hard it was shot. Holy crap! So like a gun went off in the kitchen. I go out there. Not only did it blow the cork out, it bounced all over the kitchen because it's rubber. It shot out probably half a cup or better of liquid. It just blew it out of the cup. Anyway, your minds might do that.
Okay.
Now,
I'm ready.
when you are doing this, remember, what is that y? That y that you're solving for is the y that what? It is the y that gives you zero slope. Equilibriums. Yes? All right. Now remember, back in the day, it was all about the discriminant. Am I right? The discriminant? And in the discriminant here, what had to be true? But it had to be non-zero. Yes? It had to be non-negative, I should say. Non-negative. So, what would happen, let's just check this out. What would happen if this minus this equaled 0? What would happen? Well, let's find out. So first of all, I would get 4 equals 0.08 h, and then I would get h is equal to this, whatever this is. I don't know. I can't do that in my head. 50? 50. H is 50. Well, that's weird. Now, let's look at the slope field, shall we? So, in other words, we're saying if we had dy dt is equal to 0.02 y, 100 minus y, minus 50, what would that do for us? Let's go find out. So I'm going to go look at the old slope field generator. Slope field generator. This one. You can't not think of it now, can you? 0.02 y. Okay. Well, what? Oh, because look, check it out, friends. I'm going to go from 0 I'm going to go up to 100 because we said that was our initial equilibrium solution, yes?
Yeah.
Just for fun? And make slope field. Oh. Oh.
Those all numbers?
Now, what's that?
That vertical column, is that just a bunch of numbers?
Where?
Is it?
Oh, those are just numbers. Yeah, I think, yeah. And now remember, that's going from 0 to 100. This is not very good resolution, but what does that look like right across from there?
It looks like an equilibrium.
At where? At, well, I don't know. See, so let's come back over here. Let's come back over here, and let's look at our notes. And so we said that this piece here, if it was 50, interestingly enough, that would make this piece here 0, correct? But what would that leave us? That would leave us -2 over -0.04, which is what? What does that come out to be? No. Is it 50? I don't know. Is it? It should be 50. It is 50. Yes? 50. So what are we saying? We are saying that there is how many equilibriums now? Oops, where did it go? How many equilibriums does it look like there is right now? It looks like there's one equilibrium, and it's right here. And look, it either goes down away from it, or it comes down towards it, meaning this guy is what we would call either semi-stable or a node, yes?
That's 50. Yeah.
0 to 100. That's 50. It's kind of crappy resolution.
Oh, I get it.
Does that make sense? Now, we'll do a better one here in a second. Now, wait a minute. That's if it equaled 0. Now, back in Algebra 2, we said that when you look at, ax squared plus bx plus c, and you look at b squared minus 4ac, if b squared minus 4ac equals 0, then you have one solution, yes? Right? And in other words, one solution for this deal means that there's one equilibrium. And where was it? In this case, it was at 50. But what if I want it to be bigger than 0? All right. Well, if it was bigger than 0, how many solutions would I have? 2 solutions, and which in this case would mean 2 equilibriums. Right? Interesting. So, yeah, that's great. So we said that 50 was as big as it could be, yes? If it was any bigger than 50, we'd have a problem. Right? So let's go smaller. Let's go 20, shall we? Let's go like 20. How did you know that, Mr. Grimm? Because anything greater than that would be hunky-dory, yes? Yeah. So, or I should say that anything less than 50 would be great. Right? So let's come back to our equation, which was, I'll just go right to the math, scooperoonie. Let's put this back to 20 now. Oh, 20. Weird. Cool. I see 2 equilibriums now, one up here somewhere, which is where compared to 100? Less than 100. And I see this one down here, which looks to be a skosh bigger than 0. So when I start harvesting fish out, that means I'm going to have more than 0 fish in the pond, right, in order to keep a stable amount in there, right? So it's going to be more than 0. It's going to be less than 100 to pull this off. These are going to pull towards each other until you get to where? The 50, right? Which one there's just one equilibrium at that point. Yeah? And then you can just keep screwing with this a little bit. Now, you could change this up.
What if you're taking like one fish?
Oh. Well, it'd be different. Oh, you want me to put it in there? Oops.
Is that going to make them farther apart?
Yep. And as it approaches 50, they're going to approach each other. Okay? Yes?
Do they approach 50 at the same rate?
It's a great question. I have to think about that somewhere. I don't know. I have to think about that. It's a good call. It looks like it, though. Now, you're wondering, what are those, Mr. Grimm? What are those solutions? And I tell you, I don't know, but I bet I can find out. So, back to our notes over here. I'm on 35 right now, for instance. Do you see that? I'm on 35 right here. So sweet. So let's go to the notes and plug that in. So, dy dt, of course, is negative 0.02 y squared, correct? Right? Plus, is it 2y? And then minus 35. How do I solve this? I don't know. Negative 2 plus or minus the square root of 4 minus a times c all over 2a. So give me a solution for that. These two solutions will be the equilibrium solutions. they will exhibit the same equilibrium ideas that 0 and 100 did, right? But they'll just be shifted towards each other, is all. 4A, oh, did I forget a 4? Sorry, thank you. 4AC. There we go. Good call. Good call. Yeah.
So when we say that we have the discriminant is 0, what we're basically saying is that there's one real solution and one imaginary solution. And when
No.
it's the 0,
No! It's 2 reals. It's a double root.
With every other odd.
It's back in the day, the vertex was on the line, right on the x-axis. It's a double root.
Okay.
You can never have. That's heresy. You cannot have one imaginary. That's a problem. Imaginaries come in pairs. What'd you get? What'd you get? What?
I still, to continue though, if it's less than 0, like when you plot it in
Well, no, we're not. We're going there now. We're going there. Oh, we're going there in a second. We're going to go there in a second. No, yeah, you'll see. It's going to be exciting. It's easier than that. What did you say?
Are you the one that's saying the quadratic formula?
Somebody in one of our classes.
Good Lord, no, I didn't sing the quadratic formula.
That's what I said. You asked me.
I told you that I told you to divide by 2 and square they do for completing the square.
We approach it the same way.
Good. They should. They should. Why? Because it's a quadratic.
One of them is 77.386,
77.386.
and the other one is 22.613.
I know. Because it's a freaking quadratic. I just kind of lied. I was going to use that in a second. It's a quadratic, of course. The zeros move in, right? They stand on opposite sides of the equilibrium in the middle of the vertex, yes?
Yeah.
Now, what do you do, Mr. Grimm? Mr. Grimm, I want to take out 75 fish out of this pond. What do you think? What's going to happen to my fish?
They're going to throw that.
Well, they're going to go away. So listen, so watch. 2 things. Put it down. You don't need a calculator for this. You know that 50 was the most we could take out, yes? You take anything more out than that, what's going to happen to our fish? This is pragmatically what's going to happen to them. Now, you know they're going to go to 0 and stop. But if you look at the slope field, what do you think would happen? They're going to go to negative infinity. That's right. Or whatever. See ya. See ya. And how many solutions will we have, or equilibriums? Well, when you come back over here, you know there'd be no real solutions, right? There will be no real equilibriums. In other words, there aren't any. Okay, that's a beautiful thing. In the real world we live in, who cares about imaginary crap? A lot of times. So in this case, no, it's not. And so that break-even point, that where 50 is, right there, right? That's the point. If you go on either side of that, this whole idea is what's called bifurcation. And we're going to talk about this quite a bit in the next few days. I'm going to make part of a video about this. And we'll talk about the application of it. But it's the idea of when you have, especially, most of the time, it's like 99% of the time, it's done with logistics. And you're going to have a logistic equation, something along the lines of this. Ky m minus y minus h. Okay? And when you take this thing and you stick it into the quadratic formula, so you know this is going to become negative ky squared plus kym, or kmy I should say, minus h, right? And when you plug that in, set it equal to 0, then it's negative km plus 1 minus. By the way, we will see this quite a bit again later on when we get to second order differential equations. It's a little different applications, but we'll actually run through it very similar kind of a deal like this. Corey, I like the look on your face. Yeah, but stay tuned. It'll be fun, I promise. So it's km squared minus 4 times negative k times negative h. All over negative 2k. So the value that makes this thing equal to 0, that's that bifurcation point right there. That's the point. That's the break-even point, right, if you will, right there. If you go less than that, you're going to get 2 nice, beautiful solutions, and everything's hunky and happy-dory. And if you go the opposite direction, you're screwed. You killed all your fish off. Okay? As it's called bifurcation. So the term that we don't know is going to be h right here. Okay? It's all going to be about h. As soon as you determine what h is, then you can go, okay, I need to go less than that. If I go less than that, my fish are going to be happy. Then the question is, well, how happy do you want your fish to be? Do you want them to stay pretty close to 100? Or would you like them to come down a little ways? Are you okay playing it off, all right? And then, of course, then it becomes a political deal, all right? We need to catch more fish to make these people happier, these people happier, what have you, okay? So, but that's the gist of it. It's called bifurcation. It all hinges on K right here. H, rather, I should say. It all hinges on H. So you solve for H. Once you solve for H, then you plug this value back in, right there. You plug it back in, and then you solve for Y, and you're going to get two values of Y. And usually books call them, I think, M and H. Most books do. I forgot to check what yours call them. But one of them is going to be the maximum, and one's going to be the lower values of your two equilibrium solutions. Okay, so like we just did with 76 and 22 or whatever it was. Danger Dan, what's your thoughts? Hit me. So if you're playing along, we skip kind of over 1.5. I'm going to make a video on that. It's very straightforward. 1.6 is equilibrium stuff. You already know it. Do it. And then we kind of started talking about 1.7 a little bit, but not a whole lot. That's the micro. Oh, I know, right? I know. Check it out. Check it out. Let's look at that one. Okay. So x depends on itself positively, and it is affected negatively by the other population. Okay. Let's show that here. This guy, the y's, are affected negatively with themselves. So if they get more y's, then it's affected, it's decreasing, it's trying to hurt our herd a little bit. But the other one increases our herd. Okay, so which of these is more like wool? Is it, do wolves benefit from having more wool going on? I don't think so. But they benefit from sheep. This looks like wolves to me. Okay, so the more wolves there are, it makes a big impact on the wolf population. Versus, the more sheep there are, it impacts positively. Up here, the more sheep there are, right, it really affects negatively, right, how many sheep I have, yeah? And but it also affects what? The amount of wolves I have negatively affects. Yes. So I'm going to say, that's prey, that's prey.
This is the rate at which it changes though, so like this is finding at a greater rate than multiplying that.
Yeah, don't kind of. It's more along the line. You just really look. It's pretty much that first piece. Okay, that's the basic deal. And then after you look at that, you're like, okay, well, wolves, there's more possible. And then, oh look, and look, and then it's affected positively by us. Okay, that's the way I got it.
Pretty cool stuff.
All right.
So if we like plotted that
Yeah.
on the complex plane, it wouldn't mean anything then?
The solutions I just got, or what?
Wouldn't mean anything?
No, not that I can think of.
I know in a lot of forms of engineering, using imaginary numbers is very useful.